Okay, good morning, everyone. So you've made it to the final section of the course. Congratulations. So as I said on Wednesday, we are now going to be looking at infectious disease models for the rest of the course. I study infectious diseases. That's what my research is all about. So this is my main area of interest. I'm going to be learning about some different types of models, but mainly based all around this idea of compartmental models, where we're breaking down a population into these different classes that represent disease status. So we're going to start off with something called the SIR model, and then we'll look at some variations on this in the next couple of lectures. We're going to talk about concepts. This whole area is known as mathematical epidemiology. We'll talk about a few different terminologies, things like incidence, function, source of infection, different types of transmission, whether it's density or frequency dependent, and average infectious period today. So there's quite a few different things to cover. Okay, so the key sort of aim of mathematical epidemiology is to use mathematical models to understand how infectious diseases spread within and between populations. And if you think about mathematical evolutionary epidemiology, it's taking that one step further to think about how those infectious diseases also evolve. And we'll cover that a little bit in the last week of the course. So today we're going to meet this fundamental framework known as the SIR model. And that SIR model, S stands for susceptible. So this is my susceptible class. If I can spell susceptible. Susceptible. Or S class. I have an infected, I class, and a recovered, which is sometimes just called removed population, or R class. And then we have processes that move us between these classes. So you can think of these as being different buckets. Individuals in the population are put into one of these buckets depending on their disease status. They start off as being healthy and susceptible. They can then get infected. They can then recover and become, in this case, immune. And so moving from the S to the I class, we have infection. And from I to the R class, we have recovery. This is pretty much the simplest framework that we can have. You could even just have an SI framework if you want, where there's no recovery from infection. But this is the most common sort of baseline framework that we have. So this is also known as a transfer diagram. We've met schematics a little bit like this before. These can be quite useful in order to think about the flow of individuals between these different compartments. Okay, so we'll see variations on this, like an SIRS model, where individuals recover, but then they lose immunity and become susceptible again. You could have additional classes in here. We'll meet a case where we have an exposed class and you go via this exposed class here before becoming infected. So this is an SEIR model. So there's an exposed or latent period where you're infected but not yet infectious. And in this class here, you're infected and infectious, so you can infect other people. And we'll also meet another type of model where we don't have any immunity, but you do recover. Once you recover, you become immediately susceptible again. So there's various different ways in which we can build off this baseline framework in order to cover different scenarios for different types of infectious diseases or different populations. And really, these are the fundamental models that we use during the pandemic or any sort of infectious disease outbreak to understand and predict where things are going. So anytime during the pandemic, you would have seen models of infectious diseases or on the news or predictions about what's going to happen. There probably would have been something similar to this, maybe a bit more complicated, where there are different classes like maybe individuals who are asymptomatic or symptomatic. You could build in some risk structure here or age structure into these models. They're still the same fundamental ideas. So where did this come from? A little bit of history. A couple of Scottish scientists, Kermack and McKendrick, first proposed this model in the early 1920s. Well, 1927, not early 1920s, early 20th century. And back then, didn't have computers to try to model infectious diseases. They were interested at that time in looking at plague deaths in Bombay. So this is a screenshot from that paper. So this is plague deaths over several weeks. And they developed this SIR model and then plotted the curve that came out of this against the data. So it's a little bit hard to see, but the dots are the data in the background, and then the white circles are the fitted curve. You see that even though we've got a relatively simple model, we end up having something that is pretty good fit for reality. Like, I think this is sometimes unappreciated as to how simple the model is for the complexity of populations, right? You know, these work better in larger populations. But even so, you know, people have different types of contact rates. People have different behaviors. They have different susceptibilities, perhaps. They have different responses to infection. All of these different things you can still simplify down into a relatively simple model. And this kind of, you know, stayed, you know, people were aware of it, but it didn't really pick up again too much until sort of the 1980s, 90s by Bob May and Roy Anderson. And at the time, this was the time of the HIV pandemic. Lots of people were thinking about, you know, we need to make these more and more complicated models to capture all of this, you know, behavior in the population. We need all of these extra details to really understand what's going on. And they said, actually, yeah, we can still make pretty good predictions with these very simple models that only need a few parameters and therefore are relatively straightforward to parameterize. You know, this model here maybe only takes 2 or 3 parameters to parameterize, whereas, you know, you might have one that has all these different bells and whistles, account for different types of contact rates and susceptibilities and all of that, and that might require hundreds of parameters. So really their insights were saying, okay, simplicity can really tell you something very useful. Okay, so what does this model look like? The most basic SIR model without any demography. We'll come back in a few lectures to talk about demography, that's births and deaths. But without births and deaths, if we've got a closed population, our susceptible class changes dsdt according to an infection term. So we have minus beta si, and I'll refer to this as f, function f of s and I. And this beta here is known as the transmission rate, or sometimes the pairwise transmission rate. This here is following density-dependent transmission. I'll talk a little bit more about what I mean by that later on. But this is just like the kinds of terms we saw before in our predator-prey models, right? This is a Holling type 1 response, essentially. You can almost think of the infectious class as being like a predator of this susceptible class. Our equation for the infected class, didt, is going to equal beta si. So individuals are getting infected. We're not losing any of them, so it's exactly the same term, just changed in the sign. And then we're going to assume there's a recovery rate. Here we're going to assume there's no disease-associated deaths. And this is just now f of si minus gamma I. So gamma is going to be our recovery rate. We're assuming that individuals immediately become infected, and they once they become infected, they are immediately infectious, and they also recover at a constant rate. Oh, yes.
So would we call the top one negative f of si then?
Thank you. Yes, I've missed off the negative sign. Thank you. Hi. And then finally, our recovered class drdt is just going to equal gamma I. So we've not met systems of equations where we have more than 2 state variables. Now we've got 3 state variables, but it turns out that we can reduce this down to a 2-state system, which we'll talk about in a moment. Okay, so this is the basic model. We only have 2 parameters, this recovery rate and transmission rate. And I believe we could just go back to these data here. If I recall, there were only 2 parameters in this model. So it's pretty good to be able to fit those data back in the early 20th century with 2 parameters in this model. Okay. So let's think a little bit about some of the assumptions that go into these models, because it is very simple. It means that there are lots and lots of assumptions, okay? So what kinds of assumptions are we assuming? I'll open it up to you guys. There are lots of assumptions that go into this. Can you think of any that maybe apply? Either about the infection itself, based on these equations, or about the host population. Yep, Scott.
I think the host population is not changing.
Yeah, as in there's a constant population size?
Yeah, like the total number of
exactly, yeah. So here we've got constant population size. We'll talk a bit about this a bit more in a moment. So constant population size. Well spotted. What else about our hosts? Okay. Yeah.
There's no way they jump from susceptible straight to recovered.
Sorry, there's no way. Yeah, so they don't gain immunity by any other ways. Okay, so I'll say immunity only through infection. So there's not anything like natural immunity. There's nothing like, well, unless they could start in theory off on the R class, but there's no things like vaccination. Anything else? Okay, so think about something like if I was to, maybe I'll talk about myself. If someone was to cough or sneeze on you, then, are you immediately infectious? No, it takes time. There's time for it to that pathogen has to replicate in your body before it can get to a point where it's able to transmit, right? This model doesn't have any like latent period, that's called, right? So as soon as you get infected, you can infect someone else. Okay, so no latent period in this model. What else about the host population? Think about, if you look around any room, you'll see variation, right, in people. People also live in different places, right? So there's some spatial structure. Here, we don't have any variation in our hosts. So all hosts are treated identically. There's also no spatial structure here because of that as well, right? There's no distinction between hosts. They're essentially just all moving around like gas particles in a glass vessel. Okay, so no host variation. And also we say that they're randomly mixing. Sometimes you'll see this as well mixed. That basically means that, we're saying that the population is kind of moving around, everyone's interacting with each other enough that you can treat them as being like gas particles in some container. Obviously, if you wanted to model an outbreak in somewhere like Vancouver, that might be a reasonable assumption. If you were modeling it in Canada, you wouldn't be expecting people in Montreal to be infecting people in Vancouver, right? So you might want to take into account that people don't have the same contact rates if they're not geographically close to each other. We said as well at the start that there's no host demographics. And this is a reasonable assumption if your epidemic is taking place over a relatively short space of time, okay? Especially in something like humans and in a large enough population. Over the course of, a winter flu season, say, the host population, the human population, doesn't change that much in size. Okay, so some people die. If you had a case where there was, I'm going to lead on to the next one here, we have no disease mortality. If it was killing lots and lots of hosts, or if it was over a much longer period of time, we might want to take into account host demographics, especially, if we're thinking about something over many years in the human population. And one more thing, what happens when people recover? Yep. Yeah.
If they don't fall back.
So yeah, exactly. So we say that there's full permanent immunity. This is fairly reasonable for things, say, like measles. Once you get infected, you won't be infected again. But lots of things like, coronavirus, if you get infected with that, your immunity will wane. The picture's a little bit more complicated by that because SARS-CoV-2 is evolving rapidly as well, so it's also evading immunity. But even if that wasn't happening, the immunity does wane after a period of time. They're also often in, say, sexually transmitted infections, things like gonorrhea, chlamydia, there's no permanent immunity. So after you recover from them, you're immediately susceptible again. Also, if we think like beyond human populations, we have adaptive immunity. Lots of animals and plants, they don't have adaptive immunity. So once they recover, they're able to clear an infection, they just have an innate immune response. They don't have any built-up immunity to that. Okay, so lots of assumptions go into it, and you can see, even though, going back to this point about how well these models work, even with all of these simplifications, we can still get something that works pretty well. Okay, so let's think about some of the components. Today, we're really focusing on this model construction rather than analysis, so what actually goes into this. So let's think about the force of infection, first of all. So if you recall, we had this F of SI, and this we defined to be the incidence function. I didn't actually say that at the time. This is basically telling us the rate at which new infections are being produced. So the rate at new infections being produced in this model is beta SI. Beta is our transmission rate, S is our density of susceptibles, I is our density of infected and infectious individuals. We could just write this as function lambda of I times by S. So that's just lambda I is equal to, lambda of I, sorry, is equal to beta I. And this lambda is known as our force of infection. So you can think of this as being, if it's the per capita effect on every susceptible individual in the population. This is changing because it's a function of the number of individuals that are infected. But if we say, each susceptible individual has this, experiences this force of infection. So this will go up if there's a higher transmission rate or if there's more infected individuals. Okay, that should make sense. We can also break this down a little bit further. We can think about this as being the product of several things. So first of all, we can think about, how does a pathogen transmit between individuals? Okay, first of all, we need to have some contact rate for our susceptible individuals. Okay, so they're moving around in the population. How often are they coming into contact with other individuals, regardless of their disease status? Note that this could be different for individuals who are infected. So contact rate of susceptible individuals, the proportion of those contacts that are infected, and that's just going to be density of infecteds over the total population, so I over N. So given they come into contact with someone, what's the probability that individual is infected at a given point in time? And then given they've come into contact with them, which is these first two things, what's the probability P that a contact actually leads to transmission? It leads to a successful infection. Okay, so we can therefore write this force of infection as being the product of these things. So we have our contact rate, C of N. We have our, I'll write this I over N here, our proportion of contacts that are infected, and then P is our probability that a contact is actually able to transmit. So then we can equate these two things here, connected by this green arrow. That means we can write our transmission rate beta as our contact rate times by the probability of transmission divided by the population size. So typically we'll just give, we'll think about beta as a transmission rate, but think of it as also being composed of these different things. Okay, it depends on the contact rate, it depends on probability of transmission. These things are all host dependent. Right, the probability of transmission is also pathogen dependent as well, but the contact rate is, say, host dependent. So you'd expect different host populations, say different population densities. If you're, in Tokyo, for example, as opposed to out in Prince George or something like that, the population density and things like this will affect your transmission rates. Okay, so this is an example of density-dependent transmission because as the densities increase, the transmission rate will also increase. So we can think of that in terms of our contact rate C of n. If the contact rate between individuals increases linearly with population size, then we can write this C of n is just some constant, I'll call it C1, times by the population size n. So this you can then write as lambda of I is equal to, well, we're just going to substitute this C1 of n into what we had on the previous slide. So instead of C of n, we have C1 times by n times by I times by P over n. These n's will then cancel. So we just get C1 times by P times by I. And therefore, our transmission rate beta is just the product of this contact rate, per capita contact rate C1, and the probability of transmission P. So I drew a little sketch of this before. I'll just zoom in, I'll do it here again. You think of density-dependent transmission as being something like this, where we have susceptible individuals in some area or volume. They behave randomly in the well mix. They move around like gas particles. And then we have some infected individuals given by these red dots. And then whenever a red dot comes into contact with a blue dot, then there's a probability P that there'll be transmission. That contact rate C behaves a little bit like raising the heat of a container that has gas particles in, they'll start moving around more, okay? So this is very closely related to ideas about particle movement. These things are all moving around randomly. They bump into each other at a given rate, and then if they bump into each other, then in this case here, that green dot would become a red dot now because it's become infected. And the density dependent side of this obviously means if I increase the density of either a number of susceptibles or infected individuals, these contact rates, the number of contacts that occur, and therefore the number of infections that occur will also go up. So greater population densities should lead to a higher incidence. So like I said, this is known as density-dependent transmission. It's also referred to as mass action. So it follows the law of mass action. So about particle movement. And this is usually pretty good when we have things like airborne diseases, things with direct contact, so influenza, COVID-19, and a thing that, if you imagine being on a busy bus service and someone is infected, they're going to infect lots of people. You'd expect things to transmit faster there than if you were, again, in like a rural area where the population density is perhaps lower. Did you have a question or were you just raising? Okay, so let's contrast this with something called frequency-dependent transmission. So here we assume that this C of n, this contact rate, was proportional to the population size. So we had C1 times by n. What happens if instead this contact rate is just a constant, C2? So it's not actually a function of n anymore. No matter how many individuals in the population we have, this contact rate per individual remains the same. So in that case, our force of infection, lambda of I, is now going to be, we call it C2. We don't have an n here anymore. We just have P, our probability of transmission, And then I over N, our proportion of contacts that are infectious. So we can't actually simplify this anymore. Now our transmission rate is going to be our constant contact rate, C2, times by our transmission probability P, divided by our population size, N. So this is a bit different to the previous slide. So before we had beta is equal to C1 times by P. Here we've got beta is equal to a constant C2 times by P divided by N. When might this apply? Well, this is known as frequency dependent or proportionate mixing. The basic idea for this is that as a population increases or varies, we don't see a big change in contact patterns. There are certain cases, particularly for things like sexually transmitted diseases, where you don't expect the number of, if you're in a city compared to a town, you don't expect the number of sexual partners to go up by 100 or 1,000-fold for individuals. Okay, they might vary a bit, but they remain much more invariant to population size and population density. So yeah, HIV, for example, if you wanted to model that, you wouldn't be using a model up here like this with density dependent transmission, because if you've doubled the population size, you double the transmission rate. Okay, but you wouldn't expect doubling the population size would double the number of sexual partners that people would tend to have. Okay, so frequency dependent transmission is usually used when we have things like sexually transmitted diseases. So if you sketch a graph of these two things, density dependent and frequency dependent transmission, realize that's not how you spell dependent. If we've got our population size varying here, N, and we think about our contact rate, C of N, this blue line here is showing our density dependent transmission rate varying. So when we've got very small population sizes, the transmission rate tends towards 0 because it goes through the origin. It's just a constant times by N. Whereas the frequency dependent one just stays flat. So just to check you've been listening. So does the SIR model from earlier have density or frequency dependent transmission? If I go all the way back to here, is this density or frequency dependent transmission? Someone who doesn't usually answer.
Density.
Density, thank you. It would be frequency dependent if this was divided by N, like this. Okay. There are some interesting things that come out of and consequences of density and frequency dependent transmission. We'll see if we get time to look at these a bit later on in the course. One of the key things here is that you can see that the transmission rate, because it depends on this contact rate, as the population size gets very small in density dependent population size populations, the transmission rate will tend towards 0. That means that there'll be some critical threshold as the population gets smaller and smaller where an infection can't be sustained. That kind of makes sense, right? If you're, if you've got something like flu, if you don't come into contact with someone very often, and then there's nowhere to pass it on, and you recover before you infect someone. This is especially important as well in like solitary species that only come together when they mate, for example. They might spend most of the year apart from each other. If we compare that to frequency dependent transmission, as the population size gets very, very small, there's no drop off in the transmission rate. So that risk of infection remains. This turns out to be really important when you think about the potential for infections to drive their populations extinct. We can see just from this graph here, if a pathogen has density-dependent transmission, it should never drive its population extinct. It could drive it to very low levels, and in theory, something else like stochasticity, random effects could drive it extinct, but it will always go extinct before the host goes extinct, at least in a sufficiently sort of deterministic population, okay? If we ignore effects of random effects. Whereas a frequency-dependent case, say a sexually transmitted infection that kills its hosts, because there's no drop-off as the population size shrinks, a frequency-dependent infection can drive its population extinct, whereas a density-dependent one cannot. So we might be able to come back to that a little bit later on. We'll see if we have time. Okay, so this was density dependent transmission in our original model. Okay, see how much more we've got to do. So the other parameter that we had in our model, we've talked a lot about transmission so far. The other parameter on our model deals with recovery. So we refer to these as being epidemiological processes. So transmission is one type of epidemiological process, recovery is another. And we've seen that there's a constant per capita recovery rate, gamma. This is positive. What does this actually mean, though? Well, if you think about any sort of ODE, when we're looking for solutions of these ODEs, all the way back to when we were looking at our very first simple continuous time models, we end up with solutions of the form e to the something times by t, right? Because we're in continuous time. What that ultimately means is that when we have a term like, let's just scroll down, there we go. If we have our infectious class and we have some infection terms, which I'm just going to ignore for now, if we didn't have any new infections and we just had recovery, we'd have a minus gamma times by I. This, if you just had the IDT is equal to minus gamma times by I, this would give you exponential decay, right? You would have something, a solution, I of t is equal to e to the minus gamma of t times by some constant c. Okay, this gives you exponential decay. So this also tells us then that the average time spent infectious, average infectious period, is going to be 1 over gamma. So if we think about lots and lots of individuals in the population, we could plot, not much space on this graph, but I'll do it here. If we thought about their infectious period, so how long they spend infectious, and we think about, number of individuals. So let's put this down as the frequency of individuals. Because this is exponentially distributed, you'd have a curve that looks something like this. And think about, okay, if we pick individuals in the population, this is individual 1. They have a very long infectious period, say. Individual 2 over here has a very short infectious period. Individuals 3 and 4 are somewhere in the middle. Over the whole population, you can come up with some average. There's an average infectious period according to this distribution. And that's given by 1 over gamma, where gamma is your recovery rate. It turns out the variance of this is 1 over gamma squared. So this is, again, it's quite a strong assumption to be making, but it works quite well. Again, if we think back to those data from the Kermack-McKendrick paper, this works surprisingly well. Why is it potentially a bit of a problem? Any thoughts about why this exponentially distributed recovery rate and hence exponentially distributed infectious period is a problem for some pathogens?
Derivation is 0.
That's potentially, yeah. You have an issue where some people think this is going to asymptote up here and this is eventually going to asymptote down here, right? It means that there'll always be some people that have really, 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 really long infectious periods, which would be going up this way, or there'll always be some people that have an incredibly short infectious period. There's also quite a bit of variation here. If we think about individual 1 and individual 2, yeah, you get variation within infectious diseases, and this is probably why it works reasonably well. But say if we think about something like, flu or COVID-19, most people have an infectious period around 7 to 10 days for these things, right? There's some variation either side of that, but if you were to, sketch out what is the average infectious period, I'm going to do it the other way around this time, which is a little bit confusing. But if we had our infectious period on this axis here,
and the frequency. I probably should have sketched the other one this way around as well. You'd maybe expect something a bit more like this that's normally distributed, right? That there's an average infectious period here. Most people have this, and then there's a bit below and a bit above. You wouldn't expect this to be exponentially distributed and looking something like this, which is what we have. So that's quite a strong assumption. So it doesn't necessarily work that well when we have a narrow window of recovery, when most people tend to recover in, say, something like 7 to 10 days. So let's say infections may have a typical window of recovery. 7 to 10 days for COVID.
So it's not necessarily, this doesn't really match up mechanistically with maybe what we would think happens in a lot of cases. If you have something that has a really, really long infectious period, then you can reduce this rate, but you'd still always have some people that recover very, very soon. You can overcome this by making the model a bit more complicated. One of the ways in which you can do it is you can have multiple infectious classes, and people transition between these infected classes, and that has the effect of changing this distribution and making getting something that looks a bit more like a relatively narrow window for recovery. So there are ways in which you can do it. It's kind of good to know that this is an imperfect approach. Okay. Scott already identified that we have a constant population size. If we let our population size, we already talked about this, n is just equal to our susceptibles, our infectious, and our recovereds. What happens if we want to find the NDT? So what is the change in the population size? So the NDT is just going to be dsdt plus didt plus drdt. So we have minus beta si plus beta si minus gamma I plus gamma I, which equals 0. So n is constant. So if you're not sure about whether a population size in these models is constant or not, just add up all the classes. Individuals have to be in one of these classes. So add up all of the classes, and that will give you the NDT, so the change in the population size. It's equal to 0, as it is here. Then we have what's called a closed population. There's no flow in or flow out of this population. When I say flow in and flow out, that flow in would be things like births or migration, and flow out would be deaths or emigration. So our population size is constant. I wasn't sure how quickly I'd go through some of these things, so I set this up as a self-study problem, but I think you guys can have a go at this now if you'd like to. Have a go first of all non-dimensionalizing the model by dividing each compartment by the total population size n. So we know that n is a constant thing now. If it's not varying, we don't need to treat it as a variable. We can treat it as a parameter. So rescale the population sizes, each of the classes by n. So for example, I would let u equal s over n, v equal I over n, w equal r over n, and also rescale time by our infectious period, as stated here. Have a go at doing that to non-dimensionalize the model. And then the second stage here, think about the fact that you've got a constant population size. We've got 3 equations here. What does that tell us about reducing this from 3 equations to 2 equations? And I realized that third question is actually question number 1. So you don't even need to do that one. So essentially non-dimensionalizing the model. And in doing so, we're going to be thinking about these u, v, and w variables as being the proportion of individuals who are susceptible, the proportion who are infected, and the proportion who are recovered.
So it's the same process as we were doing, with our resource competition models or with our predator prey models with rescaling them. But there, because we had two species, adding the two species together didn't make any sense really, except giving you the total number of individuals. These variables now will give us the proportion infected rather than the density infected, say. So have a go at that. You've got about 9 minutes. If you want to have a go at that, I can go through it at the end, or if we don't have time, I'll leave the notes online. Okay, would you guys like me to go through it quickly before the end, or do you want to keep working on it? I have a show of hands who wants me to go through it. Okay, that's most of you. Okay, so let's do the first bit. Let's non-dimensionalize by time, the time scale first of all. So we're going to let little t equal gamma, so that's our infectious, 1 over our infectious period or our recovery rate, times by original time scale t, then dt, big T, d little t is going to be 1 over gamma. And so we can write our ds d little t is going to be ds d big T times by d big T d little t, which is going to be minus beta si over gamma. Likewise, we can write di d little t is now going to be beta si over gamma minus gamma over gamma times by I. So the gammas in front of the I disappear. And then the rdt is going to equal, again, gamma over gamma times by I. So we've eliminated gamma as an independent variable. So gamma still appears, but it's appearing always with the beta, which means that we're going to ultimately be able to write this as just one parameter. Okay, so that was this part. Then if we also let U be the proportion of the population that's infected, V be the proportion that's, susceptible proportion that's infected is going to be V, and then W is going to be the proportion that's recovered. Notice that we don't actually have R appearing anywhere in this, because once they become recovered, nothing happens, but we can still write everything down in this form. So du dt is going to equal, well, du dn is going to be 1 over n. So we're going to have 1 over n times by our ds dt from above, which was just minus beta si over gamma. And then if I do my parameter substitutions, or my variable substitutions, I should say, we're going to have 1 over n times by minus beta. S is just u times by n, and v is I times by n, so we're going to have an n squared times by u times by v over gamma. This n out here cancels with one of them up there, so we just end up with minus beta n uv over gamma. And since n is a constant, I can write this as minus r naught times by uv, where r naught is beta n over gamma. We'll talk about this more next week. This is known as the basic reproduction number. This is the most important quantity in mathematical epidemiology. So that was my equation for susceptibles. For the infected class, I'm going to have beta si over gamma minus I times by 1 over n. If I do my substitutions, I'm going to have the same substitutions I had above because the beta si over gamma term appears in both of these equations. So I can write this down straight away as just r naught uv. And then the I over n is just v. So we have r naught uv minus v, which we can just write as r naught u minus 1 times by v. And then finally, our recovered equation dw dt is going to equal just I over n, which is just v. Okay, second, so the model's been non-dimensionalized. This second question here, using what we learned about the population size, because it's constant, we can eliminate our recovered equation from this model. In fact, we could eliminate any of them if we wanted to. We're going to eliminate the equation for W here because N is equal to S plus I plus R, and that's a constant. If we know S and we know I, and we know what N is because it's constant, then we know what R is. Okay, this is just an equation in one unknown. So we can always write R as being N minus S minus I. And likewise, we know that U plus V plus W as proportions are always going to equal 1. So if we know what U and V are, we know the proportion susceptible, the proportion infected. By just process of elimination, we know what the proportion is that's recovered. So W is just going to be 1 minus U minus V. And so although we've got a system of 3 ODEs here, we can essentially eliminate this last one here. We don't care about it because we know we can learn everything we need to know from these two equations. And we know how to deal with systems of 2 ODEs. Okay. That's it for today. Have a great weekend, and I'll see you on Monday.